And now we express our hope. Right? So we hope that something holds true. And what makes us mathematically precise is our specification of what exactly we hope for, and then maybe we can make an attempt of say exactly when that hope realizes. So what is that we hope for? We hope that if we increase this number n, if we make the interval shorter, the approximation becomes better. Right? So this number will approximate the unknown. We still don't know what that area is, right? We hope this number will approximate the area better if n is larger. And the larger n becomes, the better the approximation is. That's what we hope for. And then, to make it precise, we say that we hope that the limit of those approximations as n goes to infinity exists. Right? And we hope that it is equal to the limit of the midpoint approximations. Because it would be embarrassing to have one computation, one result if you compute left-hand side, a different result if you compute midpoint, and maybe different if you compute right-hand side approximation. So we hope for that consistency, that these limits are all the same, and we hope that it is the same as limit of sums when you choose some point in the interval, f of xi times delta x, and I would say that here that delta x goes to 0 instead of saying that n goes to infinity. And those are equivalent requirements. So we hope that this limit exists, all these limits are the same, and then, if that happens, we say that this limit is called the area. This is what we call the area. So if these limits exist and they are all the same, we call the limit the area A. Because all the way until this point we didn't know what area A is, and this is just one of possible definitions of what it is, right? We can possibly introduce many different ways to compute the area, and those don't have to be equivalent. So maybe for different shapes, well, for strange shapes, not like circle, but for some strange, really strange shapes, different ways of computing areas will result in different things. But usually we don't worry about it because usually the shapes we deal with are nice, and the functions we deal with are nice, and that's one of our assumptions. We understand that in calculus we will deal with nice functions. And there are different ways to say exactly what nice means. We usually assume functions are continuous, and we usually assume they are differentiable, and usually assume that they are differentiable as many times as we want to, right? Which is far from reality, but for the purpose of using calculus as a tool, we have to make that assumption. Otherwise, calculus just doesn't work, and you have to apply some different techniques. So, having that assumption, having assumed that the function we look at is differentiable, one can prove, one can argue that these limits exist, they are the same, and That's how we can determine what the area is. And then, of course, if you try to come back to geometry and look at some shape, like circular shape, then you have to reduce that geometric question to the question of calculus. You have to describe that shape as graph of a function, and of course for this kind of shape you cannot. So you have to cut this shape into pieces and compute separately the area above this line, because it is going to be graph of a function, the area below this line, a graph of different, using graph of different function. So there is some work to be done, but we can imagine how to do it, and sometimes this work is not easy because the shape is strange. Right? You have to cut this shape into many different pieces. But again, you have to repeatedly use the idea of additivity, that if you cut into finitely many pieces, the area is additive, and once you come up with a nice piece, then you use integral to compute it precisely. And of course, you hope that the shape of the region is not very, very wiggly, right? So you assume that geometry is not bad.